Okay. So in concept learning, basically, we're trying to decide whether a particular idea or concept has certain instances in it, right? So we can think about an enumerated set of items like coffee or tea, and then decide whether particular items belong to that set or not, right? Well, let's say whether a friend prefers certain drinks or not, right? So we can think of this as, again, some type of hypothesis space, right? Some large set of instances that are out there, and a hypothesis is just basically a coloring of that, right? To basically say, are certain items selected or not, right? That's one hypothesis, right? And so having all the hypotheses possible is usually not plausible. There's, in many cases, even if you have a finite set, like in this example here, is quite exhaustive. It's difficult to exhaustively enumerate them. So it's best to try to come up with another representation of a hypothesis, okay? And one that we talked about is conjunctive learning, right? The conjunctive learning algorithm or learner basically says the hypothesis that I care about are conjunctions of values on particular attributes, right? Like I have a value of a drink, and maybe that value is, for example, coffee, right? I could say that this person prefers coffee. For milk, they might prefer it with evaporated milk, etc. Right? So those are values on the attributes, okay? So I think most of you got that already. So let me just go ahead with that. Let's see, where's the annotation? Okay, good. That didn't clear. Okay, that still didn't clear. Hold on. Okay, I don't know what's going on. Okay, so we'll go on. So what we want to do is basically represent a hypothesis, and we can do that using conjunctive learning, right? As basically some type of constraint, right? So if you have a disjunctive learner, some of you asked about this, right? A disjunctive learner says that instead of having a conjunction of things, maybe I have a disjunction, right? I like either coffee or tea, or some of the other attributes, right? So that type of learner makes different types of assumptions on what it can represent. And because of that, we have a type of bias, right? We are saying that a particular learner only admits certain types of hypotheses in his hypothesis set out of the total space of concepts that can be represented. Okay, so for example, in this conjunctive learner, it's quite easy to see here that in this case, right, we only prefer drinks of this sort, right? Any type of drink with any amount of sugar, any types of strength, but it must be iced and it must be for here, okay, something of this sort, okay? So then the next thing is that we need to be able to describe each of the instances, right? So we have all of these different attributes, and we're going to assign values to them, or a don't care in some cases, okay? And let me get to some parts, right? So we also highlighted this important fact that in concept learning, most of the learners are going to assume that you have a noise-free environment, right? That all of the attributes and values and the labels associated with them that learners being provided with are actually correct, right? So you can imagine a case where your friend likes coffee one day and then the next day decides not to, right? So that type of noise in the data won't lead to a successful result, obviously, for concept learning and other learners, right? So we're making this assumption that the data set is noise-free. Okay, so I mean, this is a really good slide to understand what we're talking about. We have a whole bunch, in many cases, especially as soon as we get out of concept learning and into anything else like deep learning, linear regression, we basically have an infinite number of hypotheses, right? You can even think of a simple linear algorithm, okay, which has an intercept as well as a slope to characterize a line. And both the intercept, like y equals mx plus b, right? The b and the m have an infinite number of values, right? So that means the hypothesis that it can come up with, like this line that you can tilt between different places, is going to be remarkably different in, it can take an infinite number of values. So this is an idea that we want to put forward first, right? Is that we have possibly an infinite number of hypotheses, okay, in this rectangle box here, hypothesis space. And then out of all of these things, we are going to try to pick out the hypothesis that represents the target concept. There's something in that entire space if the learner can represent it, okay? If, let's say, we have a conjunctive learner and the preference that my friend has for a drink is actually conjunctive, okay? Can be expressed with a conjunction of constraints can actually be modeled, right? Then we will be able to capture it, right? So hopefully the target concept is somewhere within this space, right? There will be other hypotheses that are outside of our space, right? Because, for example, those particular instances are just not possibly represented by the learning algorithm, okay? So in a conjunctive learner, like we said, a disjunctive learner won't be able to represent some conjunctive cases and vice versa. Okay, so picking the right learning algorithm is really important, right? Like it says over here, right? Other learners will have a different idea of what a suitable hypothesis is, right? And then by taking this sort of rectangle of the inductive bias, what we feel that the concept should represent, it's going to help us get an idea of what things we can move towards in our search for the correct hypothesis, okay? So you can think that, different learners may have different hypothesis space, and some learners will overlap, like a disjunctive learner and a conjunctive learner will overlap when there's only one particular constraint, right? So there'll be some overlap in many cases here. Okay, so again, we talked about this a little bit here, but the whole point is that we want a learning algorithm that is able to generalize, right? And what we mean by generalize here is really simple, right? The whole point that we need to make sure that the instances that we observe during training, our data set D, are representative of what we want to learn and generalize for new instances, okay? So there was a discussion a little bit through some of you on the forum as well as on the videos to say, what happens if the data set changes, right? Let's say, I'm doing a recommendation system, for example, as a project, okay? And I'm doing e-commerce items, but suddenly, there's the World Cup event or something virtual online, some Twitch event, okay? And there's going to be a big uptake in the types of items for that, okay? Then obviously my underlying data distribution has changed, right? So when that changes, we may not be able to get this to be true, right? We would say our training set has it's a historical information, but it's drifted to something new, right? So that new characteristic may not be representative of our old training data. And if we keep on using the old training data to predict things, the inductive bias coming from the learner, and then also with the parameters induced by the training algorithm, the learning algorithm, may not match, okay? So things are off. Okay, and there are many ways that we can fix this. One of the ways that we're going to fix this is through validation, which we'll discuss in week 6, right before midterms. Okay, all right. So yeah, so I think we'll just talk a little bit about the feasibility of learning, because that was something else that you guys had a question about, right? So we talked about this idea that learning by itself, without making any a priori assumptions, is going to not work, right? Because the problem is when you get a test instance, okay, whatever that test instance is, well, it could be a positive instance or it could be a negative instance. We just think of it from a binary standpoint, right? Okay, so if you agree with that, there's no world where you couldn't say it's positive and you couldn't say it's negative. It's plausible, right? May not be logical, but it's possible. right? Okay, then there will be cases in which a particular model won't know what to do, right? Because if you don't make any assumptions and you've never seen that instance before, you have no choice. You won't be able to classify it, right? Because half of the models that are out there in your hypothesis space will say, yes, that particular instance is a positive example, and half of all the hypothesis remaining in a learner that doesn't make any pre-assumptions are going to say it's false, it's negative, okay? So that's hopefully easy for you to see, because there will be a very large space of possibilities, and exactly half of them will vote for yes, and exactly half will say no, right? Because those are all the possible values you could have for this Boolean case, okay? All right. So given that, we really need to have some way of characterizing learning. And that means we have to assume something about what we think is feasible, okay? What type of learning do we want to do, all right? And how are we going to set the parameters or the algorithm to encode that bias, okay? Later, we're gonna see that we believe that many times we want our features to correlate well with the problem, okay? We also want those feature values not necessarily to be too wild in value. Okay, that refers to regularization in week 5. Okay, so all of those things are going to play a role in how we structure our models. Okay. So we said that concept learning is going to be a type of search, right? We're just going to look through all the possible hypotheses that are admitted by a learner, and then try to narrow it down, collapse the space into a smaller set, and we introduce some notation. So one thing that we said that was confusing to many of you, which is in the original textbook from Tom Mitchell at CMU, is this idea of a null symbol, right? So this null symbol basically says that, you know, we don't allow any attribute values, okay? Everything is dispreferred, okay? So when that happens, basically, you cannot have any positive instances, right? Because every instance that you get will have some value in that slot, right? So for example, if you think that the first slot, which is about the drink, coffee or tea, and you say no, that means you don't like any drink, right? That all drinks somehow are dispreferred. Okay, so that's why this collapses to a single distinct hypothesis, which is this null, and then all of these other ones contain all of the other possibilities, right? Actual value or you know, anything goes, the wildcard value. Okay, so we talked about this also as a way of structuring the space of hypotheses, that if we have the idea of don't cares, meaning the question mark, right, which allows any value, somehow those are more general because they're not specifying an attribute, right? So if they're not specifying an attribute, then we can say that more specific hypotheses are somehow more narrow, right? They belong in the darker boxes on this case. Right? So then we can structure this as a lattice, right? So you see that on the right over here, where the upper bounds over here are the case of more specific hypotheses, and we have the more general ones at the bottom. And we can basically use instances to traverse this learning space, okay? So we want to define this relationship over here that defines some type of partial ordering between all of these. It's not a full ordering, as you can see, because it's a lattice, as you see on the right, right? It's not fully ordered, it's topologically sorted, that's all, okay? And then we get to some definitions about what we mean by general or equal to, and we come to the first concept learning algorithm, which is FindS, right? So FindS basically finds one of the most specific hypotheses, there could be several of them, to find out something that satisfies the entire data set, okay? So we're saying we're finding a maximally specific hypothesis by going through all of this, okay? And what we do to search is just go through this algorithm, right? Which is going to discard or narrow down the hypothesis when it comes to a new example that is going to refine what we want to say about what is accepted, okay? So I think we ended there for the first part of the lecture. Okay, it's about 18 minutes in. And so after we run FindS, we have gotten a maximally specific hypothesis, but of course, you know, it's just a hypothesis. We don't know whether it actually fits the target concept or not. Okay, and a very important thing with all of the concept learning algorithms that, including candidate elimination and FindS, is we won't know whether we get inconsistent examples, right? We can't tell whether it collapses to a null value. Okay, all right, good. So let's break there. And I'm gonna try to take some of your questions on that. So let's see, let me try to get our participants list up.